Hey team, we are in week 11. Okay. Again, I know nobody signed up for a DE course, certainly not DE 2480, certainly not DE learning mapping and GIS. Um, but that is the circumstances we find ourselves in today. Oops, sorry about that. And I think the key thing to remember again is just that we have a ton of flexibility available to us over the coming weeks. So don't hesitate at all to reach out to me and just let me know what you're going through, how things are going, and we can work to accommodate what's going on in your life right now, okay? We are certainly in unprecedented and exceptional times. Um, so although some of you might want as much normality as possible, and I am trying to provide that by keeping us up to speed with lectures and assignments, some of you are just not in a position to accommodate that or to continue as if we didn't have a major public health crisis in front of us. And so just don't hesitate when you can to reach out to me about that. So it just so happens that in the midst of this major public health and social crisis that we were already scheduled to talk about interactive mapping on the web. So moving away from mapping on our desktops to mapping online and in ways that don't require us to have expensive, clunky, proprietary software such as ArcGIS and ArcMap. Okay, so in as much as it is possible to say, we find ourselves in quite a coincidence. Okay, so we were going to be looking at web mapping anyway. It just so happens to be the case that the only kind of mapping we can do right now is web mapping. Okay, because we don't have access to our ArcGIS software anymore. What I want you to do, first things first, is to press pause and to go find me a web map. Okay. In particular, I want you to find me a map-based dashboard for some topic of interest. Okay, you're going to have to do this for Lab 5, or we're asking you to do this for Lab 5. And it is going to be a quiz question we are going to ask you. Okay, so there are points associated with this. Please go find a dashboard related to something that related to some topic of interest, and that you hope to map as part of Lab 5. Okay, so I can give you an example. We'll talk more about what a dashboard means shortly, but we've already seen many of these in class already, and you've probably already seen many of these in outside of class. Okay, just a quick example. I'll give you a couple quick examples. The first one is this. Okay, this is maybe not something you've seen outside of class. Okay, it's a little bit unique, but this will interest many of the ecologists and physical scientists, physical geographers in the room. But this is a map, a dashboard, map-based dashboard that shows us essentially how streams and rivers in the U.S. state of Texas are doing. We have points representing stream gauges, and these are colored according to how much water is in the stream or river, essentially, and whether that is kind of typical, below normal, above normal. Okay, and so this is really helpful if you are interested, if you manage, say, the water supply for a city in Texas where water supply is a concern. Maybe not much of a concern to us here in Ontario. In a more temperate climate, but in Texas, semi-arid conditions, yeah, you want to know, are the streams still running? And so, this is a useful kind of interface for certain kinds of decision makers, those who work for public utilities, water utilities in the U.S. state of Texas. where they can go and access this information about water in the streams, um, to help them make decisions about whether they're going to need to stock up on water or not. Um, it's also very useful information for ecologists to know, um, how the streams that they monitor are doing. Okay, so a lot of users can get a lot out of this different example, and it's way easier to share all of this data online in this format than passing around shape files between everybody. Imagine if the USGS just had to like send shape files to everybody who wanted to access this information. They'd be up all night sending this data around the state and around the world. Okay, where they could just build this map and yeah, maybe let people download the data, but just already map it for them essentially. Makes it much more convenient. Okay, so this is it's going to go to it live right now. Okay, so we get a sense of how this works. Okay, so this might look familiar too, depending on whether you've done the demo for Lab 5 and for ArcGIS Online already. But look at this base map. This is the default base map for ArcGIS Online. So it's kind of giving us a clue that this is all running behind the scenes on Esri's ArcGIS Online software. A much advanced version than we have access to, but ultimately probably made with the help of Esri. Okay, so we can change the base map, of course, just like we can in ArcGIS Online. We can even add some overlays here that would be really relevant. Okay, so add more of the river information for the state and the country. Of course, this is what we'll call a slippy map. I can click it and drag it. Okay. Which wasn't always the case with the web maps that we had, right? And I can zoom in and out. Okay, I can even have it pinpoint my location here if I shared my location, but I don't. So it's not going to pinpoint me on the map. I'm not even in Texas anyway, so that's not particularly useful. But for those who don't necessarily know where they are on a map, this kind of thing makes it useful. I'm going to block that. Yeah, good. Okay, and so there's all sorts of information here. These are just different layers that have been added onto this map in order to help decision makers make sense of how much water is going to be in the streams. I've talked about water supply and how that might be limited, but of course flash flooding is concerned here. So, being able to track on radar forecasts and whatnot. This is all brought together in a online medium that is much easier to share with the world and share with decision makers than, ArcMap, right? Where you're essentially limited to individuals on their own desktops working and downloading their own data. This kind of does a lot of that for them, okay? So I'm going to pop back in here and set us up for discussion. We're going to go through what is a web map. We've already seen quite a lot of detail about what they are. We're going to talk about what you can do with them, how they work, and how you can make them. And we'll also get into some advanced topics as well towards the end of today. Okay, so I just, offered you this kind of complex example about water supply and in the U.S. state of Texas as an example of what a web map is. But here's the much better example. Okay, Google Maps. I feel like probably everyone has used Google Maps or some sort of online mapping utility before. Okay, this has become as commonplace as, say, email or whatever. Even if you haven't used Google Maps, you may have used a ride-sharing app that requires you to, pinpoint yourself on a web map. You may have used TripAdvisor or Yelp that allows you to use a web map to find restaurants and other, entertainment activities, so on and so forth. Okay, so we should all be somewhat familiar with at least a kind of web map, okay? And Google Maps in particular is what we would call a reference web map. Just as we have reference maps and thematic maps, we talked about that distinction way back in week 1. We don't get away from that when we talk about web maps. This is a reference map because it is just showing us what is in Guelph, or what is in Canada. There is no particular theme to this map. This is just showing us what is where, okay? But the kind of difference here is that, well, not only can we zoom in and out on this map and kind of look at things at different scales much more quickly. Sorry about that. This is on a timer that is held over from a previous iteration of delivering the presentation. So we might get a little bit of that today. But what's so unique about web maps and Google Maps in particular is that we can personalize them fairly easily. Google does this behind the scenes for us already, so it kind of pulls in information from our other tools, our apps in the Google sphere. So you can see on this map, it's pinpointed a location for me already. I have some sort of event there in March, okay? I pulled that in from my calendar, okay? Which you might think is creepy that it automatically does that, but at the very least, there's a lot more integration with these kinds of maps. This is another kind of web map, okay? Again, a kind of reference map maybe, although the theme here is traffic cameras. So there is a theme. Behind it is a base map for the city of Toronto, which is a kind of reference map. But this is another example of a web map. You can access it through the city of Toronto. They want you to know where the different traffic cameras are. We have thematic web maps that look a lot similar to the kinds of things we were mapping in Lab 3 and even in Lab 4, okay? So, this example right here is just a kind of basic one that was put out by the New York Times a few years ago. The theme here is, favorite basketball team, okay? So this is data from Facebook, the number of likes for each team based on the county of the individual doing the liking. So we can find out that in Wellington County, Ontario, most of the likes that we have offered here go to the Raptors, no surprise there. Second place, the Heat and the Lakers, maybe no surprise there as well. Okay, so this is all done on the web. This is a map that still exists that you can go and interact with. Zoom in and out and hover over to retrieve information about each county and who their favorite basketball team is. There's some issues here on this map that I think you probably are already picking up on that we'll come back to later, but just maybe the obvious here is the projection, right? This does not look like what I've told you all is a good way of projecting data throughout the entirety of this course, okay? And we'll explain why that is later on, why they've chosen this really crummy projection for this map. Some more examples, okay? Just very quickly, like we can do any kind of, all the kinds of symbolization strategies that we've looked at in this course, we can do online, okay? So these are just a few examples of how we would take some data that we have and make bivariate choropleths or different kinds of bivariate thematic web maps. This is that same data, favorite team by county, limited to the US. And this is a web map, but it is not interactive. Now, most of the web maps that we think of, like Google Maps or the previous basketball map I showed you, those are interactive. You can zoom in and out, you can drag across the map, you can hover over things and retrieve information. This is not. This is just a static image. Okay, and you could access it on this site here. But this is just a static image. It still counts as a web map. It is made for the web. It is a map on the web, but is not interactive. So there's a difference here between web map and interactive. Sometimes they go together. Often they go together. Not always. Okay. What can you do with one? At the very basic level, you can execute daily life tasks with web mapping. Okay. Maybe in a way that you can't with ArcGIS, right? So you're probably not going to use ArcMap to calculate the best way to get to work. Although you could, and if you really wanted to nerd out, you could, and you could do a whole sort of analysis of like, what's the best way to get it to work based on topography and road network and so on and so forth. You could do that in ArcMap. More likely, you're going to go to a web map like Google Maps, plug in your address, and that's how you're going to get to work or school, right? So, executing tasks is a very basic function that we have with web maps. Presenting information, okay? You can certainly use ArcMap to present information, to, export in PDF or PNG graphic form a map that you make about some data, right? You've already done that in multiple labs in this course, okay? But this is something that web maps are really excel at as well, okay? And there's a whole host of them here at the Guelph Geodata Hub. So this is the city of Guelph. They have a bunch of spatial data on like where are the community gardens in the city and where are the bus stops and so on and so forth. And they make all that available to the public at this Geodata Hub, hosted, as you'll see, by ArcGIS Online. Okay, so I encourage you to go explore that. That's an answer to the question, find me a web map, okay? And there's data there that you could use for Lab 5. But essentially, they're just showing you the data they have, showing you the information they have that the city collects. Where are the buses? Where are the snow plows even? That's a data set they have. But at another level, web maps allow you to explore the data. So not just see what's there, but to understand patterns and trends in the data set. Okay, so maybe still getting us into a little bit more advanced kind of capabilities like we do have with ArcGIS. Okay, so these are what we would call decision support tools or dashboards. These are things like the Texas map that I showed you earlier that are not just, here's the stream monitors we have, but actually allow you to, play around a little bit more to better understand better understand patterns and trends in the data. So remember, we could lay on the radar data, we could overlay the river network, we could add all this information to that stream monitor map in order to help us kind of make a decision potentially about whether we're going to get a flash flood or be in a drought. Okay. Good example here, the Nature Conservancy has put together a coastal resilience dashboard that allows you to look at and explore. We'll see this in a second, but is my house on the coast going to flood? And will it under this scenario? Will it under that scenario? So on and so forth. In maps, web maps also engage people. So this is often called crowdsourcing, where we take information that people have provided on the web from one form or another, maybe from tweets they've made or from Flickr or images they've uploaded to Flickr, which if you don't know what Flickr is, it's like the Instagram of 10 years ago, or even contributions made to the city of Guelph's Geodata Hub. They've requested people to just kind of weigh in on what makes Guelph awesome, or to pinpoint locations on the map that make Guelph awesome. Or even a really great example that I wish I would have pulled up the example of and I will, but just not right now. In the wake of social distancing, one of our PhD students in the geography department has put together a crowdsourced map of which restaurants in the city are still open and doing takeout business. Okay, so that is a kind of crowdsourced map because the data was produced by the community, just weighing in and helping him build that data set. Okay, and it was a way to kind of engage people in making that map in the first place, rather than just me, the expert, making that map. So let's take a closer look at some of these more advanced techniques and options like exploring data. So this is a web map that this US state of Louisiana puts out. It allows you to explore flood risk in the state over time. Okay, and as you might expect, red equals a higher flood risk or more storm surges expected, and blue is maybe less risk of storms and flood surges in the future. Okay, and so you can actually dig into this a bit more by some of the information here on the panel in a kind of legend. So you can get the legend about how many feet are expected to flood and so on and so forth. But you can also toggle data on and off. You can explore it. You can say, well, under the medium scenario, what does this look like? Or under the high scenario of climate change, what does flooding here look like? And what if it's not just a 100-year flood, but a 50-year flood? These are all different ways of exploring data that's already been produced, but that is publicly relevant and that everyday users like you or me might want to know about. Okay, so those are just some examples of how we would execute exploration on a web map. Time for a formal definition of what a dashboard is. And I'm going to read this straight through because I spent a lot of time thinking through it, and I think it makes a lot of sense. Coordinated compilation of maps, charts, and other information. That's key. Maps and other information like charts and text in one frame. So one site, not a bunch of different tabs and other websites you have to load up, with the goal of facilitating holistic awareness and or decision making around a topic, be it flood risk in Louisiana, be it flood risk in Texas or drought risk in Texas, or risk of infection to coronavirus. Okay, so you all may have seen this. This is one of the most famous maps that's been circulating around coronavirus over the past few weeks. This link here. Again, you'll notice it's built on top of ArcGIS Online. Can't get away from it. But this is the Johns Hopkins University dashboard. Okay, so this is one page. When you go to this website, this is what you see. It's not scattered in different tables elsewhere on different pages. It is a dashboard. It's like the dashboard of your car. That's where the term comes from. It's got all the things you need there to toggle on and off to explore your data. Okay, so we have a coordinated visualization here where we have different visualizations of the same data. So not only do we have it by country and the size of the point symbols indicating the number of confirmed cases, but over here we have that data displayed temporally, not geographically, but temporally, where we see the confirmed cases rise over time over the past couple months. So this is a dashboard. As an aside, and extra credit for anybody who wants to explore this, dig into this a little bit further, feel free to email it to me or reach out and let me know your answer in any way, and I'll give you extra credit for it. But what's this deal? So if you play around with this dashboard and zoom in and out, and you can, this is a web map that you can zoom in and out and retrieve information on, just like that Texas water stream gauge map. So you can mess around with it. And one of the things you might notice is that there's this dot off the coast of West Africa for West and Central Africa. There is no country there. Why is that dot there? Why is that data there? Anybody who can answer that question right will get some extra credit. It's a very interesting case in geospatial data and how we process it. Okay, that's all I'll say. This is another dashboard. This is the Toronto robberies data we've been working with, but here it is displayed in a format that is supposedly more useful for decision makers. So again, it's a dashboard because we have our map, but we also have the same exact data displayed in different ways. So in charts and different kinds of tables, so on and so forth, okay? And this is supposed to, point out some patterns to us. And, you could dig, if you were a decision maker with the Toronto Police Service, I'm sure this could help you, figure out some patterns. I would have to spend some time with it to really know what the patterns are. Other than that, if you look here, there really aren't that many robberies in the wee hours in the morning compared to late at night. Great, glad we learned that. So those are some examples of dashboards, and again, those try to bring together all the information we have on a topic in one place to help people sort of understand the situation better, whether it's coronavirus or crime in Toronto, and potentially to make some decisions around it. So maybe if we look at this, we might decide we're going to increase policing at nights because we know that's when most of the robberies happen. On to how these web maps work. Okay, so these maps are coded into the website's HTML. That stands for Hypertext Markup Language. And that is essentially a programming language, kind of like Python, but one that is specific for building and displaying the websites, most of the websites that we interact with on a daily basis, okay? Now, there are two different ways that these web maps work. All the ones, I'm pretty sure, most of the ones that we've seen so far have been built with what we call tiles, okay? And I'll get back to that in a second. We're going to spend plenty of time on that. There are other kinds of web maps that we can create that are built with a canvas approach. And in this approach, essentially your browser, Google Chrome, Firefox, whatever, Safari, when you land on a website that has a web map, your browser will do the work of actually drawing out the outlines of all the geospatial data that you have. And the advantage of that approach, there are some challenges to it. It's harder to program. The benefit of that is then we can, because the browser is drawing it when you land on the site, we get to do a lot more with projections. We get to choose the right projection for our map. But most of the web maps that we see and that we make in the world and that we will make for Lab 5 are going to be based on what we call tiles. Okay, so the base maps are going to be based on tiles. So all of the base maps that we've seen, like on the Texas water map and the Toronto robberies map and the John Hopkins dashboard for coronavirus, all those were built with what we call tiles. Google Maps has tiles. And these are usually pre-drawn geographic data that are projected in the what we call pseudo Mercator or web Mercator projection. And we'll talk a little bit more about what that means in just a second. But essentially what we mean by tiles is just different images of the Earth's surface that we load as we zoom in and out on our map. So when we're at level 0, when we're all the way zoomed out, we only really need one image. That is one map, because we can just kind of load up an actual image of the Earth. But as we zoom in, we can't keep zooming in on that one image. It would need to be a really big image file for us to zoom in and get all the detail that we want. So instead, as we zoom in on our Google Maps or any other kind of, most other kind of web map, what we're doing is the web map is going and retrieving new tiles that are specific images for that area. Okay, so let's actually look at what that means a little bit more closely. So let's say we're here in off the coast of West Africa again. Okay, that has nothing to do with the extra credit thing I just announced or whatever. It just happens to be that we are going to be off the coast of West Africa for this example. So at zoom level 0, we are, on our web map. In our web Mercator projection, our web map, we only need that one image because we don't need all the detail. This is a question of generalization and simplification. Well, we're so far zoomed out, we don't need all that detail. So we just need one image to represent where we're at. And then as we start to zoom in to this location in West Africa, well, then we load the next image. We're not zooming in on this image because there's not enough detail on this image. It was meant for a very far zoomed out view. So when we zoom in, we need to load a different image. We load another tile, okay? And so since our point off West Africa is in this quadrant of the world, we load this image, which is this down here. And we keep zooming in and we load it. We load in this tile, which gives us a lot more detail for this particular part of the world. And we keep zooming in and we keep breaking down the world into these smaller and smaller quadrants that are already created images of the Earth surface at that location, okay? So it's not like we're just, zooming in on one image of the world. We're actually zooming in, and as we zoom in, we load different images that are appropriately generalized for that zoom level. Okay, so just think back to our discussion of generalization and simplification. As we zoom in, we want more detail, and so to get that extra detail, we're just loading new images that have the detail. And as we zoom out, we don't need that detail, and so we are loading images that are more simplified representations. So this is how web maps, which, as you know, are kind of defined by their ability to zoom in and out. Most web maps are interactive in that sense. This is how they work. So to sum up those tiles, I kind of think of them as grids of rasters, and in fact they are images. So each tile is usually about 256 by 256 pixels. We have 19 different zoom levels. I've only shown you 4 or 5 of them here, but there are actually about 20 different zoom levels that we have, each one corresponding to a different scale. Look at those representative fractions here. One unit at level 0 is going to be representative of almost 600 million units of real Earth space. And of course that fraction gets bigger, larger scale as we zoom in. Now I want to show you something to just maybe make this a bit more concrete. You can actually see these tiles loading, unless you have like super fast internet or whatever, you can actually see these tiles, the outlines of them loading as you go on Google Maps here. Here we are in Guelph. As I zoom out, watch the rest of the map that isn't already on the screen load in, and you'll see the outlines of these tiles. See these little, it's very quick, but pay attention to the edges of the map. As we zoom out, and we don't already have the images that we need loaded, watch them load up. You can see these square tiles loading in. And you can even see them as we zoom in too. Yep. So anyway, this is just to illustrate the concept of the different tiles that we have, and as we zoom in and out, that they're loading. Okay. Now we get to a point when we're so far zoomed in that that's not Well, one, we've already loaded all these tiles, so Google doesn't need to worry about that. So it's harder to see them when we've already loaded this layer. Okay. Now, so that kind of base reference version of the world that we see on web maps, but oftentimes we want to be loading in thematic data about, where are the robberies, or where are coronavirus cases, or where is anything else. We want to access this thematic data. So what does thematic data or layers for our web maps look like? How do they work? Well, just like in desktop GIS, just like in ArcMap, we can work with vector data. Now we can also work with raster data on web maps. I'm going to set that aside and focus on vector data for web mapping. And we know that vector data is points, lines, and polygons. Points, lines, and polygons, all right? The difference is that we don't store those points, lines, and polygons in shape files. I mean, we do, and we can, and we use shape files in web mapping, especially on ArcGIS Online, but that's actually a relatively small sample of the web maps that are out there. Most of the web maps that are out there that map thematic data, or many of them at least, are using differently formatted geospatial data, so not the shapefile format. Okay, and that's because shapefiles are a proprietary format owned by the makers of ArcMap. Okay, so that works great when you're using ArcMap, which is the industry standard desktop GIS. But when you're making a web map, especially if you're making a web map that isn't on ArcGIS Online, then you might be out of luck with a shapefile, especially because not only because they're proprietary, but because they've got 3 to 5 different files associated with them: the actual .shp, the .dbf, the .xml, the .prj, blah blah blah. And so they're not particularly easy to work with. They can be larger than they need to be. And that's not something we want for the web, where we want to get our users the data quickly, because we all have now short attention spans. Bravo to you who've made it this far in the lecture, but these days our attention span is just so limited, mine included, and so if we don't get people the data that they want on the map as soon as possible, we're out of luck. And so we tend to work with a different format of geospatial data when we do web mapping, or at least we do work with this open format quite regularly, and that's called GeoJSON. I'm going to let you guess or figure out what the JSON stands for. It doesn't really matter for our purposes, but GeoJSON, okay? Kind of a funny name, but let's take a look at what this looks like. A really great resource is geojson.io. So here we are. So we are looking at something very similar, a kind of web map reference, a reference web map for the city of Guelph and its surrounding areas. It looks different. Some of the features are drawn differently and labeled differently, but that's because this is not Google. This is what's called OpenStreetMap, which is the open source version of a Google map. But still, you can see the tiles load, the little square tiles load as we zoom in and out. Okay. They load pretty quickly because I'm lucky to have decent internet at the moment. Okay, but what we're going to do is we're going to put thematic data on this map, okay? So this web map allows us to add data to it, and it's going to show us what that data looks like in code, okay? So it's really hard to get behind the actual like format for the shapefile. Um, but in the GeoJSON format, we can actually look at what it looks like in code at a more kind of computer level. So let's add a point. We know points are kind of building blocks for vector data. So let's just add a point to the hut building here. And there we are. We've added our point to the hut building. And that's what it is. That's all it is in code. And this is code that our browsers know how to handle and process. It's a standard format. And it's much easier to work with. Our browsers are able to work with it much easier than a shapefile. So let's just break this down. It's telling us that our type, we have a collection of features here. In reality, we only have one feature, the point. And here's the list of features we have. Again, there's only one, and it's a feature. We haven't set any properties for it, but we could. And it has a geometry, and the geometry of this feature is obviously a point with specific coordinates. Okay, so we can go ahead and delete that, and let's make a line. So let's see what it would take like to get from one point of town to the other, and maybe over to here. So we've just drawn a line, and we could have drawn a much better line, but this is just an example. And we get a very similarly formatted thing, a collection of features. Again, there's one here, which is this line, but it is the type a line string, just means line, that has 3 different coordinates associated with it. 1, the starting point, 2, the midpoint, and 3, the end point. 1, 2, 3, okay? And we could add another line to this map. Same deal. And we've added another feature, a separate feature here. All right. We can do the same. I'm going to delete all these. We can do the same thing with polygons. Okay. So we might be interested in just kind of zooming in here maybe and just drawing out the buildings on campus for fun or whatever, let's say. There's a polygon. It consists of 5 different coordinates here. Now why 5? We have the starting coordinate, the next corner, and we eventually loop back in on ourselves here, okay? So we have 1, 2, 3, 4 corners, and then the last corner again, okay, to indicate that it closes in on itself, as we know polygons do. And again, we could add more polygons here if we really wanted to, draw out the hut building. Okay, this is much easier, I think you might agree, of creating geospatial data than, our shapefile. And maybe a much more intuitive. I mean, I know at this point it's still kind of hard to wrap your head around this, but at the end of the day, you can at least see how the coordinates are stored and collected much easier, I think, than a shapefile, okay? And again, it's a much lighter file. It's only 75 lines of text, so it's easier for our browsers to work with on the internet, okay? That's exactly what we have here, okay? So we got a point, looks like that, a line, 2 coordinates there, and you can't read this, but it's the same deal. We've got a square that consists of 5 coordinates. We've got a polygon, okay? Now, most web maps that you interact with, as I've hinted to previously, use a web Mercator projection. And I'm not going to get into the technical details of how a web Mercator projection differs in a Mercator projection. Well, I might actually a little, but there are a lot of intricacies. The bottom line is it's very much like a Mercator projection. It just everywhere north is up everywhere. Say unlike a conic projection, where north is only straight up and down at the central meridian. On a web Mercator and a Mercator projection, north is up everywhere. So our meridians are straight lines. All of our meridians, lines of longitude, are straight. The meridians are evenly spaced, which we know makes for distortions um, towards the poles. Okay, and so we get stuff like this where Canada is much wider and taller than it should be. Okay, which really doesn't help us for a lot of the design problems we have, such as mapping favorite basketball teams across North America. Um, this makes northern Canada and Alaska way bigger than they should be, way out of proportion, and really distracts from frankly, the more interesting parts of the map, where we can really break down by territory these different favorite basketball teams. Why do we use the web Mercator projection? Well, it turns out it is easier to calculate. And again, because this is data that is shipped over the internet, it's not just like you on ArcMap on your desktop waiting for it to load. I know that's annoying too, but because it's the internet and speed is of the essence, time is of the essence, this stuff has to be easy for your browser to calculate. And Web Mercator, it's very easy for the projection to be calculated and to load our data because we're in the Web Mercator projection. And this is how it differs slightly from an actual Mercator projection, in that we are assuming the Earth is a perfect sphere rather than an ellipsoid. So going way back to our conversations in week 3 around geodesy and the shape of the Earth, in the Web Mercator projection, we actually just say, to hell with it, we're not even going to try to assume or try to fit the actual shape of the Earth. We're just going to, the fact that one axis, the equatorial axis, is bigger than the north-south axis. Screw that. We're just going to say the Earth is a perfect sphere. So that makes calculations a bit easier to do if inaccurate. Now, I should say that Google Maps recently changed. Well, recently for me, who's been using Google Maps for 15 years. They recently changed their projection, at least when you're so far zoomed out. They now use an azimuthal family of projection called an orthographic projection when you're really far zoomed out. That gives the illusion of the curvature of the Earth. Now, web maps do what they do. That is, they enable our users to do a kind of GIS in their browsers through what we call interaction operators. We've already seen one of these, and it will be very familiar to you. That is the pan and zoom operator. I can click on the map and drag it around and zoom in and out and have fun. And that is what that makes for what we call a slippy map, because it's kind of slippery. Didn't always used to be this way, okay? So, I don't know, maybe some of you will remember something called MapQuest, although, I'm looking at the date here, and this is copyright 2003. So this is, old. But this is how, web maps used to work, where instead of being able to click on the map and kind of drag it around and just, use your cursor to zoom in and out, you had to click north and you had to click east. And each time you click these things, it would load a new page. Okay, and you would click zoom out and it would load the new page with the new map. Okay, it was the most god-awful thing ever. Okay, and so luckily we don't have that anymore, but that is, pan and zoom are fundamental operators that allow us to interact easily with our web maps. Retrieve, another really important operator. which allows me to click and get data. So I can click on a point of data on my map, a county like Wellington County. I can click it and get the percent of likes for each team in the NBA. Okay, that's an example of the retrieve operator. Filtering, a bit more complex. We filter our data all the time in desktop GIS in ArcMap. When we select by attributes or select by location, you can achieve the same sort of thing in a web map by different kind of operators that allow people to interactively, filter down to like a quantile of a range of certain data, for instance. Highlight. Sometimes when we put our mouse and hover over data on a web map, we want that to stand out more than the other thematic data still on the map. That is called highlight. A good example of that is at nativeland.ca, where you can highlight or hover over an indigenous territory, and it highlights it against the rest that are in the area. Finally, a couple of really important operators here. Re-express, so we can change the classification. We can change between, not every web map does or allows all of these operators. It's important to note, but the more advanced ones will offer all of these. So allowing you to change the classification scheme from quantile to equal interval, or so on and so forth. And sometimes even re-symbolize, so allowing you to change from the polygons that you loaded, that the data were originally into, say, points, okay? Which is all things we do in ArcMap, and that some web maps allow us to replicate. So how do you make a web map? This is where it gets a little tricky. So we have several what we call software as a service providers, SaaS providers. These also go by the term platforms. These kind of provide a lot of the backbone for us to make web maps easier, so they don't have to do all the programming yourself. Okay, so you can actually make you can easily make a web map on Google. If you have a Google account, go to My Maps. You can upload data to that, you can add markers, you can do lots of other things right there, and you can share that with people. ArcGIS, a lot of the functionality of ArcMap, but with all the windows and menus, is available to you in even the most basic version of ArcGIS online, which we are going to see in the demo. Okay, so it does a lot of the work for you, so you don't have to do all the programming. There are some more advanced. Both of these, ArcGIS Online and Google My Maps, have severe drawbacks. Okay, so they can, there's only so much so much data you can upload. They don't allow you to analyze your data in particular ways. You can't do a whole lot of GIS operations in the basic version of ArcGIS Online. You can't even do any in Google My Maps. Okay, so there are other platforms such as Carto that do allow you to do a lot more advanced GIS in your browser, and allow your users to actually do some of those advanced techniques. They enable more of those interaction operators that I just discussed. Okay, so the thing there is, even though they offer all those operators to you and your users, but they're no longer free. Okay, so you have to pay to create a map on Carto. You have to pay to create a map on Mango. Okay, so on and so forth. So that is why we're not using them in this course, is even though they used to be freely available, and I still have a free account that I can use, they are no longer freely available for users. They are instead trying to make money off of their service, which is unfortunate for our purposes. Of course, you can program your own map. Okay, at the heart of WebMap are different web programming languages, such as Python and HTML and something called JavaScript. Of course, that takes more coding skills. They do enable you to be a lot more flexible in the kind of map you make and how you make it and how you share it. Again, it takes a lot more heavy lifting in terms of coding skills. So I'm going to demo ArcGIS online now. That is going to be in a separate video, so feel free to pause here, and we'll pick up in just a second. Okay, maybe welcome back if you've come back from the ArcGIS online demo. If you were just following along from earlier in this week's lecture, then here we are again. We are talking about how we can make web maps. Okay, so you've seen the ArcGIS online demo. Again, some of those web programming languages that I talked about. You've already started to learn Python. That's great. That's going to be really useful for you in web map programming. Again, some other ones, HTML, JavaScript, something called CSS. Even beyond that, to be even more, some more advanced languages here that give you even more opportunity to do some powerful mapping. Something called SQL. I actually mentioned this last week. We do work with this a bit already in ArcMap. It's called structured query language, and it helps us work through the data we have, filter our data, query our data in relatively straightforward ways. There are other database filtering and querying languages out there. SQL is the most common. Just as with Python, there are tutorials out there on how to start coding and doing the kinds of coding that will let you help you build incredible web maps in the future. LinkedIn Learning, which you have free through the University of Guelph, is a resource available too to get underway with that. CS 1200 and 1500, also great courses taken. Now for Python, we mentioned that 1500 is probably the course you want to take, Intro to Programming. CS 1200 is more Intro to Technology in general. The reason I recommend it here is because they do a lot of work around, building a website, learning HTML and CSS and maybe even JavaScript. So for web mapping specifically, I would actually recommend 1200 if you have the opportunity to take it. Perhaps you have the opportunity to take 1500 as well. And then, independent studies. Okay, so I'm actually working with a student who a year and a half ago took 2480 and now is working with me in an independent study to do some web mapping. So, these opportunities are available. And, my general advice for how to keep learning with a particular topic or language or software or tool or whatever is to, just pick a problem that interests you. Maybe it's, at this point, it's probably not crime in Toronto, but maybe it's, maybe it is mapping coronavirus, something that is just really on your mind and that you want to learn more about. Use that as an opportunity to sort of as grist for learning more about the actual tool and developing skills around that tool, language, or software. Okay, because you'll be more invested in learning that tool, language, or software if the product at the end of the day that you come away with is something that's interesting to you, that is a topic that excites you and isn't just something dull and boring like Toronto crimes. I want to make a plug here. So we just have one more little section to go through when it comes to web mapping and mapping in general, frankly. And these are a bit more advanced concepts, but that, in this line of talking about, scripting and programming, are important to be aware of because these are increasingly things that employers and others want to see you develop at some point in your career, okay? And so one of those is the ability to work with databases, okay? And so I will put a plug in here for a course that I'm teaching this fall 2020, called 3440 GIS for Decision Making. And I'm going to say more about that in just a second, but at a very basic level, we'll be doing things like more web mapping, and so just going beyond ArcGIS Online to things like participatory mapping and learning about what are called geodatabases. So remember this job posting I showed you for week 10 for why you might want to learn Python programming and Model Builder? Well, here you go. Another thing that they're looking for is not just Model Builder or Python, but geodatabase design and implementation experience. Okay, so I'll say more about what a geodatabase is in a second, but just know that this is something that employers are looking for in a GIS analyst, and we'll get some experience with that, not in this course, but in 3440. I will introduce it to you in just a second later today. Okay, so. This course that we're offering next fall, for the first time, what we're interested in doing is moving beyond 2480, where we've kind of given you a sandbox to explore some fundamentals in map making, and to actually now start to apply them to real world use cases, and to understand how maps get used, or maybe don't get used if they're designed improperly, in these real world use cases. So not just talking about, make a map of farmers using GIS and across Canada, although that might have its own use case. But we're going to be talking about perhaps more applicable real-world use cases, okay, for decision making. So you'll be doing things like evaluating these decision support geospatial tools and dashboards that I've been showing you, as well as applying the design principles that we have sort of overviewed here in 2480, symbolization strategies, classification techniques, so on and so forth, taking all that you've learned here and applying them to more real-world settings, to do things like communicate science around a topic that excites you, to potentially persuade decision makers, and to provoke public dialogue amongst stakeholders. Okay, so really what this is to use geomatics not just to make pretty maps of the world, right? But to use it as part of decision-making processes. But of course also to reflect critically on how those decision-making processes occur, whether it's in environmental management and policy making, or whether it's in some other kind of setting in which geomatics would be relevant, sort of maybe city planning around how do we allocate resources to look at and investigate crime in the city, things like that. You'll gain familiarity with not just industry mapping software like ArcGIS, further experience with that software, but also open source software, that the kinds of software that will be available to regardless of where you are in the future and regardless of whether you have access to an Esri license or not. And just to give you a sense of what this looks like a bit more concretely, so I'll just share a couple of the labs that we planned out already. So lab 2, the second lab, we're expecting that you'll be working with a small group of classmates, working, you pick a community partner. You might actually go through the whole steps of actually, working closely with that community partner, because that is a kind of commitment that takes a long time to develop and do right. But you can at least, we will at least have you envision working with that community partner here in Guelph or in Ontario. And we will ask you to develop a proposal for what you would map with them. so in how you would engage them in a kind of participatory mapping exercise that gets data from them and maps it, or produces data with them and maps it, or that responds to their interests and maps the kinds of things that they want to see mapped. Okay, and this is going to be good preparation for those of you who would like to take the most advanced geomatics course we offer here on campus, which is 4480. This is a course, a 1 credit course, 4480 is, that has you work in small groups over the course of the entire semester to, oftentimes with community partners, so not always, to develop a project, a geomatics project. Lab 3 that we're planning for 3440, this is where you're going to learn and get real experience with geodatabases. So you'll be, this will be an individual project, but you will be relying on your fellow students to, at different parts of the lab. So you will be a database manager at one point. You will create a database. You'll ship that off to other students. They'll ship their database off to you. You will model that data, doing what we call a multi-criteria analysis. You will then provide that analysis to other students who will make decisions with it, and you will in turn get model results from other students and be forced to make a decision based with the data that they've given you. And this is all to simulate how a GIS workflow and pipeline exists in real-world conservation and other organizations, for that matter. Okay, where you have the database manager and they've got their job. You're the modeler or you're the decision maker. Each of these parts or roles is a different person, and they have to translate data into analysis and into decision support from one to another. Okay, so you're going to get experience in that kind of setting and scenario, just like you would in a real workplace. Just as the person who has to do the database management for a conservation authority and ship that database off to the modeler, the ecological modeler for the conservation authority, who has to do the modeling and then present that information to, say, provincial planners or city planners in the area. All right. While we're on this note, I want to say a little bit about what a database is and why we might design and use a database. So at a very basic level, and ultimately get to how it's relevant to web mapping. So a database at a very basic level is a system for organizing and accessing lots of data that are related to one another. Okay, and that can be geospatial data. It can be attribute data. We use database management systems to interact with those databases. So, I kind of have this analogy of, the way this works is, we've got our data kind of in the kitchen, and we're the head chef, and we are yelling at our database management system to give us all this data because we got the users who are wanting and needing it because they're trying to visit our websites or whatever, and they need to get the data from us. And so these database management systems are kind of stuck in the middle, trying to access everything that we have in the database, make sure the right order is served, okay? Make sure the right data is returned to the right users. Just as in a restaurant, you need to make sure the right dishes are served to the right users. Okay, we'll work this analogy as we go in and keep talking about databases. But at its core, it is about serving data from the kind of back-end storage system out, serving the right data out to the right users. So, let's start with a really basic example. This is a database that stores just information about students. Okay, and we can see that these different fields here are linked to one another. So, we have one database here on the left that's students, and all these different things here are essentially, you would think of them as columns. I know they are horizontal, so they look like rows, but essentially they would be columns in our database or our spreadsheet. And, each student has a value for each column. Okay. And that's linked to another spreadsheet by this common field, a student ID. We all have, or you all have student IDs, right? So that we can store information about the classes you are taking. We wouldn't want to store all that in the same spreadsheet here because, well, each of you is taking several classes and it would just get messy to kind of try to store all of your information just in one spreadsheet. So we store the classes information in another spreadsheet. And then, that includes the ID of the class, like 2480, and then also the ID of all the students taking it, their grade, attendance, so on and so forth. And then maybe that is linked to another spreadsheet that, just says a little bit about the class. 2480, your professor's name, the room number, the time, so on and so forth. And so, a database here is a compilation of all these different spreadsheets, or what we technically call tables, that are linked together. And they allow multiple users to interact with this data remotely and to make queries of it, to find out, well, which students are in 2480 and what cities do they live in. This is actually something that universities do, is they have all this information stored, and there are researchers at the university, or there are university administrators, right, who want to know more about all of you who are here at university. And that information is available in these databases that store all this information. So we could do a query of this database that asked, well, who are the students that are in 2480 and what cities are they from? And we could figure that out ultimately, going through all these different tables on information about teachers, students, so on and so forth. This is just an example. I certainly don't expect you to memorize this. This just give you a sense of how, for an entire organization like a university, this is the kind of database consisting of a variety of different tables that they might put together in order to help them manage what happens at the university, to make decisions about the university. Okay, this is something. Again, we'll explore this more in 3440, but this is something that you might see in a conservation organization, a database of different ecological and biophysical data, linking them together and making that available to different users within the conservation organization to help them make decisions about where to invest. Okay, by making queries of that data. Okay, that is what databases are doing. They are linking together these different tables of data and enabling queries of them. It turns out that ArcGIS databases, ArcGIS is kind of a database management server or software. It is it is allowing us, the user, to access data behind the scenes, stored on our computer. Okay, so it is that kind of, the head chef who's yelling at the files and folders, the head chef yelling at the kitchen to get the right food out to the right users. That's kind of what ArcGIS is. It's yelling at our computer and the files and folders behind the scenes to give it the right data to us, the users, based on the queries that we do. That's the analogy. Okay. And you know that in shapefiles we have the .dbf. That stands for database file, dbase file. That is, again, every shapefile that has an attribute data associated with it is a kind of database. And you know, every database has limitations. There are ones that are specific to shapefiles in ArcGIS, and you've probably run into these before. So, but maybe didn't have the notion of how to describe these limitations. So, you know, we can only store so much data in a shapefile, 2 gigabytes worth of data. After that, Arc kind of gives up and won't let us store any more information than that. So each shapefile is really only limited to 2 gigabytes. It doesn't like nulls and oftentimes converts them to zeros, which we know are not the same thing. You've probably noticed that the field names, that is the column names, can only be 10 characters long, which is a huge advantage. It makes accessing, from ArcGIS's perspective, it makes accessing our data a lot more easy. But from our perspective, the user's perspective, it's really annoying because we often run into like, well, what does this column refer to? Remember I shared the example of flooding in Louisiana, the database shapefile I had where the column names just made no sense without having to look at the metadata. And it turns out you can only have 255 fields in your database in a .dbf, which is how we store our attribute data in a shapefile. Now, there are other kinds of formats in databases that ArcGIS works with. So beyond shapefiles, we have what are called geodatabases, .gdbs. And these, there are different kinds. There's personal geodatabases, file geodatabases, enterprise geodatabases. Especially the file and enterprise geodatabases are really built to allow collaboration between members of an organization. So if we were working with an enterprise database, we could essentially just have that one copy of our data, and I could access it, you could access it, we could both actually access it at the same time using a geodatabase. So you can see how that would be really useful for an organization to allow them to allow its employees or members to collaborate and coordinate like that. In the context of working from home, that becomes even more valuable. I'm sure you understand. Where you don't have to like email each other shape files back and forth as you update them. Instead, the single copy of the data in the geodatabase updates as you update and work with it. So that's the idea behind a geodatabase. You can kind of think of it as like, I don't know how many of you use OneDrive, but if you have a file on the OneDrive server, you can share that with many others. That same copy of that data, and they can update it, and it gets uploaded again to OneDrive, and then you can access those new updates. It's a very similar idea, but instead of just like a Word document as you would have on OneDrive, we're talking about geographic and geospatial data here. And so ArcGIS allows those kinds of things through these geodatabase formats. You get to have longer column names too alongside them. But essentially, you are collecting different featured data sets within this geodatabase. Okay, so at the end of the day, you might end up having a shapefile called roads that is stored within your geodatabase, but you're also going to have, you know, other shapefiles stored in environment, climate, maybe even rasters, all stored under one single geodatabase that if it's an enterprise geodatabase that you can share with others in your organization. And this is what it looks like behind the scenes in your folder. So when you open up a geodatabase using Windows Explorer or whatever, it looks like this, which is super messy and nobody knows how to read and it's completely unintelligible, but that doesn't matter because you don't need to work with these files. You work with the geodatabase itself within ArcGIS. Okay, so these are all things that we will be learning a lot more about in 3440, okay, and how to use them and how to take advantage of those powerful collaborative opportunities. Now a similar yet different sort of story applies to web mapping applications, okay, so we also have spatial databases when we're talking about web mapping, and the way that these works is it's not so much the same principle, right? Where I have some data stored on a computer or what we call a server that I want to send to you and make available to you, the world, the public, and instead of like a geodatabase where you're another member of my organization and I just want to make sure that we have access to the same file and can update it at the same time, both of us. Instead, with a spatial database for web mapping, it's more, I have a file on my computer, I need a database that can ship it off and share it to a web map that somebody's loading on my page from China or whatever. Okay, so in other words, we are letting the world get access to our data based on their queries of it. And we might even let them post data to our database. So that's a really unique thing that web mapping allows us to do, and especially web mapping that has a spatial database behind it. But we are letting people potentially draw on our maps and then submit their drawings to our database, our computer, so that then we have their data. So it becomes a much more a two-way street than a typical kind of map where we, go into ArcMap, we make a map, we print the PDF, and maybe we post it online or whatever, and then, maybe somebody sends us an email and says, hey, cool map. With web mapping, we're actually enabled to do things like share our map and then have people even, add to it, add their own sort of input, a marker, a polygon, a line. They can actually help us create the map together. So I'm going to share an example of some of that kind of mapping that I've done with the Canadian Census of Agriculture. And also just a very basic example where I allow users to contribute their data. Okay, so running with this analogy of this sort of behind the scenes or, back of the house analogy, my database is stored on some computer in Michigan, okay, in the US. That this company A2 Hosted owns. So all my data is there. It's in a database, and it's data on the Canadian Census Ag, same exact data you worked with in Lab 3. And some of that data is data that's already been contributed to the map. And users to the web map, the website that I have here, and that we'll see in just a second, they can make queries of the data, which is essentially making an order of the data. In our database management system, which is in this case called PostgreSQL, remember SQL is structured query language, it is the kind of middleman here that is yelling at the server in Michigan to retrieve certain parts of the data. Okay, maybe not all the data all at once, but based on what the user has ordered up when they visit the site to get that data, and then it ships it back to them. And this is all, of course, happening in code and in the code that I've particularly written for this this site. So to make this a bit more concrete, that I have made. Okay, so this is a very bare bones web map here. But again, what we are doing is mapping Canada's census of agriculture. Specifically, I've chosen to map the percent of farmers using robotic milking. And that is not what's showing on the map yet. Instead, this first part of the map is random shapes that people who have visited my site have contributed. So how does that work? So you can draw, a marker on my site, on this site, and submit it. And when I refresh the page, what's going to happen is my browser, this Internet Chrome or Google Chrome here, is going to request all the data from the server in Michigan that hosts all my files and data, and it is going to retrieve this new marker. Okay, so let's just see that in action. There it is. So what's happened is I have clicked on the map, I've submitted it. That is, my browser has pushed that information to the server, the computer in Michigan, and then it's there stored permanently as part of this map. And so now if you were to visit this map now, you would see that marker, and you could create put a marker of your own on here, submit it, and then somebody else could visit this map and put their own marker, and so on and so forth. So it is a way, these databases that allow posting data are a way for people from different points in time and locations to contribute to a map and comment. Okay, and it's not just markers, right? I could draw a little shape here, and of course this is totally meaningless. I'm just going to draw a shape there, close it, submit it, refresh the page, and there it is. Okay, so now let's actually get to the point that's about the census of agriculture. So as I zoom in, eventually I get to a certain point where we get this little wheelie guy, and then what's happening here is that my browser is calling up that server in Michigan and asking for that data on the census of agriculture. And it's only asking for the data that is appropriate for this zoom level, and is also only kind of within the frame that I can see here. It's not sending me data for BC, because I'm nowhere near BC right now. But I can, drag over towards Alberta and BC, and eventually, well, what happens is the browser makes a new request to that computer and server in Michigan, and it says, hey, my user is, now on the map in the prairies, and so it needs this data. And it gets that back from the server in Michigan, slowly but surely. Okay, and I scroll back, and it says, hey, we're back in Ontario and Quebec, give me this data. And slowly but surely it comes back and it says, well, here's that Ontario and Quebec data. I know you don't need the BC and prairie data anymore. Here's the Ontario and Quebec data, slowly but surely. And so this is what databases that can be queried, spatial databases that can be queried by location, offer us on the web, because we don't want to load all of Canada's information at one time. There are a lot of little census divisions across Canada, as you learned in Lab 3. You were able to load that on ArcMap pretty easily because you had a desktop. You were able to load all those census divisions across the entire country. But we're on the internet, we're on the web here, and time is of the essence, and data space is of the essence. And so we don't want to send a huge file consisting of all these little census divisions to our user all at once. Ideally, we only send them the census divisions that they're looking at in the map. And that's what the spatial database approach allows us to do. It's only sending us Ontario, Quebec, and the Atlantic, the Maritimes right now. So that's all that we're looking at. And if we do go over here to the prairies, well, then it will load us this. It will make that query the database, and the database will ship us only that data. And sure, it could be more efficient. It could load faster. We could be, more patient with it, whatever. But so it goes. Now, the same exact principle applies when I start zooming in more, okay? So, for this zoom level, that kind of sense division makes sense. But if I'm zooming in all the way to Guelph, I want more detailed data. And in fact, we have smaller census units that we can work with here. And so as we zoom in, and just a quick detour, you can see the outlines of the tiles here. Remember, that's for the base map, not the actual thematic data here. So as we zoom into the Guelph area here, or into a particular area, we load smaller units of our data. If I'm not mistaken, there are even more smaller units than this, but I don't think the map's going to show them to me for whatever reason. I could be wrong about there being smaller units. There they are, a little late. So it's not a perfect web map yet, but we're working on it. Like I said, I have a student working with me on a very similar project this semester. So if we zoom in and we stay put and we have some patience, it will eventually load us that more fine-grained, like township level census data, okay? Which is more relevant to this zoom level than these big county level things, okay? So now we're getting the data that's just relevant to this one particular area, the area we're looking at. And again, I don't know why it keeps shifting back, but hey, bugs are inevitable. And of course, if we zoom back all the way out, like at this level, and we're looking at all this level of Canada, we don't need all that little detail like right there. We can't even read that. And so what it's going to do is it's going to switch back to provincial level data eventually, because that makes more sense for this scale. And so we're able to do that with a database approach that is working with our browser to serve only the data that is necessary and appropriate at a specific time. So we did that demo. One question for you that you will see on the quiz that you will take on CourseLink. What kind of geospatial data are we looking at here? Is this how we store our rasters, how we store shapefile data, Python, or GeoJSON? So you'll be answering this question on the CourseLink quiz that is a component of Lab 5. All right, everybody, that does it for week 11. I hope you are all doing well. Again, as always, don't hesitate to reach out at any point and just let me know what's up, how you're doing, say hello, all of that. I look forward to hearing from you. Take care.